Researchers at the National Institute of Standards and Technology (NIST) have devised and demonstrated a system that could dramatically increase the performance of communications networks while enabling record low error rates in detecting even the faintest of signals, potentially decreasing the to. The proof-of-principle system consists of a novel receiver and corresponding signal processing technique that, unlike the methods used in today's networks, are entirely based on the properties of quantum physics and thereby capable of handling even extremely weak signals with pulses that carry many. We built the communication testbed using off-the-shelf components to demonstrate that quantum measurement-enabled communication can potentially be scaled up for widespread commercial use, said Ivan Burenkov, a physicist at the Joint Quantum Institute, a research partnership between NIST and the. Burenkov and his colleagues report the results in Physical Review X Quantum. Our EORT shows that quantum measurements are valuable, heretofore unforeseen advantages for telecommunications leading to revolutionary improvements in channel bandwidth and energy efficiency. Modern communications systems work by converting information into a laser-generated stream of digital. The train of pulses grows fainter as it travels along transmission channels, and conventional electronic technology for receiving and decoding data has reached the limit of its ability to precisely detect the information in such attenuated signals. The signal pulse can dwindle until it is as weak as a few photons, or even less than one on average. At that point, inevitable random quantum fluctuations called shot noise make accurate reception impossible by normal classical, as opposed to quantum technology because the uncertainty caused by the noise makes up such a large part of the diminished signal. As a result, existing systems must amplify the signals repeatedly along the transmission line, at considerable energy cost, keeping them strong enough to detect reliably. The NIST team system can eliminate the need for amplifiers because it can reliably process even extremely feeble signal pulses. The total energy required to transmit one bit becomes a fundamental factor hindering the development of networks, said Sergei Polyakov, senior scientist on the NIST team. The goal is to reduce the sum of energy required by lasers, amplifiers, detectors, and support equipment to reliably transmit information over longer distances. In our work here we demonstrated that with the help of quantum measurement even faint laser pulses can be used to communicate multiple bits of information, a necessary step towards this goal. To increase the rate at which information can be transmitted, network researchers are finding ways to. So a single laser light pulse, depending on how it was originally prepared for transmission, can carry multiple bits of data. To improve detection accuracy, quantum-enhanced receivers can be fitted onto classical network systems. To date, those hybrid combinations can process up to 2 bits per pulse. The NIST quantum system uses up to 16 distinct laser pulses to encode as many as 4 bits. To demonstrate that capability, the NIST researchers created an input of faint laser pulses comparable to a substantially attenuated conventional network signal, with the average number of photons per pulse from 0.5 to 20. Though photons are whole particles, a number less than 1 simply means th. After preparing this input signal, the NIST researchers take advantage of its wave-like properties, such as interference, until it finally hits the detector as photons particles. In the realm of quantum physics, light can act as either particles photons or waves, with properties such as frequency and phase, the relative positions of the wave peaks. Inside the receiver, the input signal's pulse train interferes with a separate, adjustable reference laser beam, which controls the frequency and phase of the combined light stream. It is extremely difficult to read the different encoded states in such a faint signal. So the NIST system is designed to measure the properties of the whole signal pulse by trying to match the properties of the reference laser to it exactly. The researchers achieve this through a series of successive measurements of the signal, each of which increases the probability of an accurate match. That is done by adjusting the frequency and phase of the reference pulse so that it interferes destructively with the signal when they are combined at the beam splitter, cancelling the signal out completely so no photons can be detected. In this scheme, shot noise is not a factor, total cancellation has no uncertainty. Thus, counterintuitively, a perfectly accurate measurement results in no photon reaching the detector. If the reference pulse has the wrong frequency, a photon can reach the detector. The receiver uses the time of that photon detection to predict the most probable signal frequency and adjusts the frequency of the reference pulse accordingly. If that prediction is still incorrect, the detection time of the next photon results in a more accurate prediction based on both photon detection times, and so on. Once the signal interacts with the reference beam, the probability of detecting a photon varies in time, Burenkov said, and consequently the photon detection times contain information about the input state. We use that information to maximize the chance to guess correctly after the very first photon detection. Our communication protocol is designed to give different temporal profiles for different combinations of the signal and reference light. Then the detection time can be used to distinguish between the input states with some certainty. The certainty can be quite low at the beginning, but it is improved throughout the measurement. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.